Okay, let's take a look here now at example number 1. I want to suppose that a lamina occupies the region D given by these xy points. It's all the x comma y's where y is less than or equal to 1 minus x squared, but greater than or equal to 0. And let's suppose that the density at any single point here in the region is always just equivalent to its y-coordinate. So if you're at y-coordinate 0, there's 0 density. If you're at y-coordinate 2, there's density 2. I want to find the center of mass of the lamina. So first thing I might do is sketch a picture of this region. So I'll say we will sketch a picture of D. All right, so let's see here. Out in the xy plane, if I'm less than 1 minus x squared, let's see, 1 minus x squared looks like this, parabola opening down. And if y's got to be above 0, then it seems like this space right here would definitely be my region D. Okay, so that's a pretty simple region. I'm looking for the balancing point of that region. Now I might guess again that the balance point is maybe somewhere smack dab kind of in what looks to be like a nice simple balance point. But remember that this density might potentially throw some things off slightly, because I recognize that again at high y values there's more density, at low y values there's less density. No big deal. Again, I need three double integrals to be calculated here. The first thing I'm going to want to do is find the mass. So I'll say we first find the mass of the lamina. Okay, so that would be m is equal to, and I'm going to do a double integral here of my density function, which is y. And then I just have to decide how I'm going to integrate that. Now, if I think about my region here, it seems pretty easy to see that I cross over the x-axis at the points of -1 and +1. So maybe I could set up the following double integral. I'll integrate y, first with respect to y and then with respect to x. Because x bounds go from -1 to 1, but my y bounds go from 0 to 1 minus x squared. So I'll go ahead and crunch this out, not too difficult. -1 to 1. I get a half y squared evaluated from 0 to 1 minus x squared. This is an integral from -1 to 1. And I get a 1/2 1 minus an x squared squared dx. This is a little bit annoying to deal with, but of course I could just go ahead and multiply some stuff out here. I think if I multiply everything out, I'm going to end up with a 1/2 a 1 minus a 2x squared plus an x to the 4th. I'll go ahead and evaluate this. My antiderivative is going to be x minus 2/3 x cubed plus a 5th x to the 5th. And I want to evaluate that from -1 to 1. Let's see. I think that's going to leave me with, at the end of the day, a 1/2 times a 1 minus a 2/3 plus a 1/5 minus a 1/2 times a -1 plus a 2/3 minus a 5th. I'll notice that if I distribute the negative through in the second set of parentheses, I get all the same values again. So this is actually really just going to be the same as 1 minus 2/3 plus a 5th. And if I simplify that out, I think I get 8/15. Okay, so I have the mass. You can double check me on that to make sure that I crunched everything correctly, but I believe that's good. So once I have the mass computed, I just need to go ahead and find out what is x bar and what is y bar. And you might recall the formulas for those that we wrote down were I should always do 1 divided by my mass, then a double integral over d of x times my row xy. Okay, so this isn't too terrible. Again, I'm probably going to set this up in the exact same way that I did just a moment ago. All right, I'll start off with 15 over 8. And I think I can set up my bounds exactly the same as I did last time. The only thing that's different now is I have x times y on the inside. No big deal, we can crunch this out. So I have 15 over 8 integral from -1 to 1. And on the inside here, I'm going to get a 1/2 xy squared. And I'm going to need to evaluate that from 0 to 1 minus x squared dx. So let's see. I'm going to get 15 over 16, integral from -1 to 1. I'm going to have x times 1 minus x squared all squared. This is a little bit cumbersome. What I'd ask you to do at this point is to see if you can go ahead and actually try to finish the calculations for x bar and for y bar and see if you can conclude what the center of mass of the plate is. When you hit play, you'll be able to see me go back through all the rest of this, and then the video will end at the end of this example. Okay, so if I was to continue on here, I'd end up with exactly this times the integral of, I think I would get x minus 2x cubed plus an x to the 5th gets me 15/16, gets me a 1/2 x squared minus 2/4 x to the 4th and a 1/6 x to the 6th. Evaluate from -1 to 1. I see here that regardless of when I plug in -1 or +1, I'm going to get the same exact value back. I'm going to get 15/16. I'm going to get a 1/2 minus a 1/2 plus a 1/6. And then I'm going to get a 1/2 minus a 1/2 plus a 1/6. And so here, my balance point is 0 for x. Maybe not too surprising that the center of mass would be somewhere on that y-axis. To find my y bar, I'm going to set up the exact same sort of a thing. The only difference now is instead of having an x times my mass, I'm going to have a y times my mass. And so I'll have a y squared in there. So when I crunch that, 15/18, 1/3 y cubed, 0 to 1 minus x squared. This is a little bit annoying for when I do my evaluation. Oops, sorry, that should be 15/8. Here, I think if I multiply everything out, I'm going to end up with a 1 minus a 3x squared plus a 3x to the 4th minus an x to the 6th x. What I've left out here is the 1/3, which I will go ahead and pull out. If I pull out that value of 1/3, I'm going to get over 24 here. Oh, wait, I forgot something else. Notice that, let me re-express this. This would be 1 minus x squared all to the 3rd. Took that 3rd out. Then I would end up with 15/24. And then I'll just rewrite that out again. This would turn into, if I simplify the fraction, I believe that is 5/8. And I would have x minus x to the 3rd plus 3/5 x to the 5th minus a 7x to the 7th. Evaluate from -1 to 1. I should be able to see here I'm just going to get double of whatever happens when I plug in 1, because when I plug in a -1, I'm going to get all opposite values. So I'm going to end up with 5/4, 1 minus 1, plus 3/5 minus a 7th. And ultimately, I get all that turns into 4/7. So as a conclusion, I can write that the center of mass is 0, 4/7. If I was to take a look at the picture, I could see that this is slightly over halfway to 1. And since I know that this function up here crossed the y-axis at 1, If this is where a half is, then my center of mass is maybe somewhere around here. Okay. All right, so we were able to find the center of mass doing these quick calculations. In the next video, we'll see how we can extend this to the world of 3 dimensions.